Right. So now, lecture recordings. I'll try recording the lectures from today and see if it works out. Okay. If it works out, then I'll continue doing this and then posting on our webpage. So exercise 1 is going to be published soon. It's going to be OOD generalization exercise. And for the next 3 lectures, including this one, I'm going to be talking about OOD generalization. Okay, so I think that's it for the logistics. Do you have some other questions, or otherwise I'll sure.
Is there already a deadline for access?
Yes, I think so. Do you think that's the fixed deadline for this exercise? Right. So it's also written on the webpage, and I think it's also written as 21st of November there, right? So, all right. So now let's get started for the content. ID and OOD generalization. Okay. So I'm repeating the table from last week, which is showing like different cases in OOD generalization. There are like 3 different cases that I consider are kind of important. These are not like comprehensive list. So cross-domain generalization means the training and test sets have different domains, meaning that, for example, you need to kind of recognize the person based on certain features, but now one of the features are kind of changing from training to test. So now you have seen the person in office kind of environments all the time, but now you have to kind of recognize the same person in party costume. And how are you going to do that? Okay. And because cross-domain generalization is kind of mixing a lot of different factors together, so I like to actually focus more on cross-bias generalization, which is exactly when the queue that's kind of changing from training set and test set is exactly the queue that that the model is likely to look at. Okay, so let's say the model is very likely to look at the costume of the person, or not exactly the costume, but the clothing of the person, right? And now, because now the queue for person A has changed from the person's own jacket to person B's own jacket, right? And so the machine is very likely to confuse this person to be person B, right, instead of person A. So this is kind of testing if the model is focusing a lot on a queue, which is kind of irrelevant to the identity of the person, basically. And this is called cross-bias generalization. Now, adversarial generalization means there's an adversary who's trying to ruin your generalization. So now this person A is an adversary against your face recognition system, which, by the way, does not mean person A is bad. Actually, person A may actually need that for hiding the own identity, right? And person A can use, for example, face mask or kind of adversarial. There are also like adversarial patterns that are designed to avoid the face detection systems, right? So that could be a good example of kind of trying to avoid the surveillance system, for example. So why do we care about OOD generalization? Self-driving cars, there are some examples of that. There were some interesting cases when you kind of crash into the bollard, because this is kind of a new arrangement that the model has not seen before, right? Who would expect the bollards to be there when you do the right turn into some street, right? Yeah. So to be sure that you're kind of good to go in a lot of situations, then you need some kind of OOD generalization. And also, a lot of things change in the world, right? Including COVID. So, so this dashed line is the sales of loungewear across time. But But now the predicted line is not reflecting the reality after some change in the environment. For example, the national lockdown, right? And then now you have even more sales of loungewear after the COVID. So how do we kind of address this kind of domain shift? So the typical way machine learning people do that is by doing model retraining. So now over time, things have to change over time anyways. And so your model accuracy will drop over time. It's inevitable. So to take care of that, people do re-annotate or recollect data and then re-annotate the data sets and train the model on that. And that's kind of supposed to keep your model above certain accuracy threshold over time. Okay, but then that tends to be quite costly because of manpower, which is around at least 100,000 euros per person per year. And GPUs plus electricity, these are also very expensive, like 25,000 euros per year for GPUs, for decent GPUs. And that uses 8 tons of CO2 per year. And now data management, managing all the schema and maintaining the working database, these are all very expensive. So now that's why there's MLOps, which is machine learning, engineering, and operations. So if there is no distribution shift, then there's no need for MLOps, in my opinion. You just need DevOps. But now MLOps involves the data curation procedure as well. And now they have to kind of take care of the shifting data versions, and keep annotators in the loop to do the annotations again, and then update the models accordingly. And ideally, you have to do this semi-automatically, so you don't need a lot of people maintaining this kind of system. So ideally, eventually, we wish to kind of get over the MLOps levels as well. So let's say the holy grail of machine learning is a greater level of automation, sorry. So level 1 is kind of no machine learning at all. And then level 2 up to level 4 is MLOps with some degrees of automation. And then level 5 is you get over MLOps altogether, right? So you just have an automatic system, which is kind of taking care of your model all the time. So in the level 1, when there's no machine learning model, then you have to kind of have a huge number of personnel, like 40, 50 years ago, in a center, and they're like processing a continuous in-stream of data with human intelligence. And this is very costly and also not very efficient. So that's why there's machine learning, right? And then let's say level 2 is a model that learns to generalize to the same distribution based on the annotated samples. So it can do in-distribution generalization pretty well. But then this does not come for free. You need to have some annotators to annotate those images. And also the world is changing. And so you need them to annotate, let's say, every month, right? You can have in-house annotators, or you can also outsource them to annotation companies. There are a lot these days. Or you can do it with AMT as well. But now you wish to kind of reduce the annotation as well. And then now we develop a model which is sort of a little bit resilient to distribution shifts. Then that can actually reduce the required frequency of annotations, let's say every year. And that's already going to reduce the MLOps cost quite a bit. And now let's say there is level 4, which is kind of the extreme of the annotation, which is you don't require any annotation at all. But still, you need some MLOps in this case, because you still need to do a bit of model selection to make sure, like you have a kind of candidate list of models, which are supposed to take care of all kinds of variations in the world. And all you have to do is to select the right model at the correct period of time. And in that case, you don't need anyone else to annotate the data again, but you only need machine learning engineers who can kind of choose the right model at the right period of time. And finally, ideally, we can even automatize that, and we can just let the model figure out which model to choose and do whatever you want to do. And then in that case, we probably don't even need any machine learning engineer. Okay. So that's sort of the general direction that we are trying to go in this domain. And cost for human efforts. This is a bit like giving you more detail of how much it costs for annotations. So annotations are something like 10 to 30 US dollar per hour. It's like slightly above the minimal salary for, let's say, for US workers. Okay. And typically for harder tasks, you need to provide more US dollars to attract the right workers. So for example, that translates to something like 1 million US dollar for collecting a data set of size like ImageNet. It has 1 million training images. Well, to be more precise, ImageNet 1K data set, training set. Okay. And machine learning engineer, they're also very expensive. Yeah, I'm repeating this. Okay. So now, so once we kind of solve the OOD generalization, then we are sure that the models will work well even under new situations, and MLOps will probably not be needed. Small businesses can afford them. You can use machine learning for more risky applications because you're sure that it's going to work in that situation. And then you can see more applications of machine learning in healthcare, finance, transportation, etc. But now what do we exactly mean by OOD generalization? Because there are so many different scenarios for OOD generalization. Okay. So now I'm going to talk about, we need the right language to express what we exactly mean by generalization or distinguish different types of generalization. And the language that machine learning researchers use for that is called settings and real-world scenarios. Okay, so the bottom line is that we care about deploying machine learning systems to the real world. And the setting, what we exactly mean by setting is the specification of resources and surrounding environment for an ML system. So in a sense, resources are kind of input to the system, and then the surrounding environment is more like where you're going to put your model in, right, in the real world. What's the real world situation? So I can give you an example of in-distribution supervised learning. In this case, the development resources for developing an in-distribution generalization system is a set of label samples, X and Y, from some distribution that is available. So you collect a lot of samples from P, and then you label them with annotators. And the deployment environment should have the same kind of set of data, not the labels this time, but data which comes from the same distribution as the development resources, okay? So this is kind of the ideal scenario that that machine learning research has started its exploration in, right? And what are the essential components when you say, when you specify a setting? So you have to specify the resources, of course, resources that are available for development, for example, data sets, samples, labels, what kind of supervision is given, guidance, explanation, tools, knowledge, or even inductive bias. These are all part of your resources for development. You can also say machine learning engineers are kind of resources for development. They have their own kind of knowledge to optimize your machine learning model in the right way. And if you have a better kind of engineers who have better intuition of what's the right thing to do here and so on, then you can train your model more quickly, right? And that's also part of your resources. Now, environment for development. What kind of distribution will the model face? I think it's a fairly simple concept. And then there's also the consideration of time axis. So because you can also have cases where the resource availability changes over time. Obviously, you need to do development first and then do deployment, right? But sometimes you can start your deployment, but then you can still do the development on the way at the same time. So to take care of all these different scenarios, we need to kind of introduce this time axis as well. A bit more terminology. So we talk about train, dev, development, test, and so on. So the one problem with machine learning is that there's a lack of consensus in terminologies. So what I would do is to just define what I mean by all of this. So development means the phase where you train your model and then make design choices. So I wouldn't really separate the training phase and dev phase, but I would separate the development phase, which is also including the training stage, and the deployment stage. Okay, so there's only two real distinction: development and then deployment. And training is the particular action of just fitting your parameters for your model. Okay. And deployment means, right, you deploy it. And then test is a little bit different from deployment in the sense that it's still part of development, right? It's kind of a lab setup, which is designed to as closely mimic the deployment as possible, right? Because some people think test set is the deployment set, but as soon as you have label samples from deployment to test your model, then you're kind of using the information from the deployment setup, and it's not generalization anymore. And the test set becomes part of your development again, right? Because why do you measure the accuracy on your test set, right? Because you wish to, for example, compare your method against the previous methods. And that's kind of implicit way of choosing your model against the prior methods, right? And that's part of model choice, design choice. And therefore, test set is, in the most precise sense, still part of development. And for deployment, you never get any annotations in reality. It's sort of a fictitious being out there. Now, the relationship between settings and real-world scenarios. So we have seen what settings mean, right? And now what does the real-world scenario mean? So real-world scenario means you come up with some kind of example in the real world where your setting kind of correspond to. Okay, so for example, let's say you have in-distribution supervised learning setting or learning setup. By the way, settings and setups are kind of synonymous words. Once you have this setup, you can kind of come up with an example in the real world where you try to build a system for detecting defects in wafers, wafers like those semiconductors, right? And they're very susceptible to kind of small dents and small defects. So they use a lot of image analysis to detect those defects, right? And let's say the development resources is a collection of wafer images with labels saying if it's defective or normal, right? You train on these kind of development resources, and then at deployment time, we assume that the images are from the same distribution as the training set distribution, meaning that you are using the same kind of camera for taking picture of the wafer images. And basically it's same setting, same wafer product as well. Yeah. And of course, you can also come up with a new setting and convincing real world scenario. So I think this is a very important kind of practice for machine learning research, because in distribution supervised learning is super simple, but once it gets more complicated, then people mean different things with different words. And it's very important to figure out what they mean by a certain setup. And then you need to ask them, what are the resources that you're assuming? And how do you make the fair comparison against the previous methods which may be using probably less development resources than you're using. So these are all very important. Okay. And now a few more terminologies. There are terminologies like environments, domains, and attributes. I think they are kind of essentially meaning something similar. But environments, okay, so environments and domains are, I would say, synonymous again. Okay, that's why I put this or here. So environment or domain describes the same distribution, describes the distribution from which your data are sampled. So for example, if you look at all these kind of distribution data sets, you see that they're kind of coming from their own data generation process. Like this cartoon is from cartoon. There are some sketches or clip arts and so on. Products, they are mostly a white background, iconic images. And what I mean by domain label is the label that you put on those kind of data. It's also kind of a data set name, right? So in this case, MNIST is domain label for this image. Sketch could also be a domain label for this image, which is in contrast to, for example, the class label, which is elephant here, right? Or clock here. So there are like two orthogonal axes here. And now there's more general notion, which is attribute labels, on which I'm going to talk a bit more later. Okay. And domain labels are a special case of attribute labels. It's essentially like attribute labels are kind of labeling all possible kind of factors that's varying in your data. And obviously your data set label or the source where the data is coming from, that's an instance of attribute label, okay, attribute. And yet there's one more terminology, which is task, which is, I think everyone kind of understands what task means in general, but more specifically, what I mean by task here is the function that I'm trying to learn, right? So for example, there can be semantic segmentation, which is kind of given an image, you wish to label each pixel in the image, okay? For classification, you wish to have a single kind of label that's output from the input image. Object detection, you wish to find all instances for each class in the image, and so on. So these are kind of different instances of tasks, okay? And now the same is true for, let's say, language processing, natural language processing. So you can have kind of sentiment analysis or some kind of machine translation, which is turning your language into another language. But I wish to go a bit further to say that even within classification, depending on the set of classes that you're trying to predict, you can say these are different tasks. So for example, for classification, there can be Pascal classes, which is 20 classes. And then there's a superset of classes in Coco, 80 classes, which is strictly containing the Pascal classes. So I would say they are different tasks, okay? Now, let's talk about different settings in OOD generalization, having established all the terminologies here. So, so there's time axis, development first, and then deployment, okay? And again, ID generalization means you have the same domain all the way through. And you have label samples, of course, for development. But now at deployment, you have unlabeled samples to generalize your model too, okay? Now, OOD generalization generally means you have some domain for development and then some domain for deployment. And now you have label samples and unlabeled samples. So you have some kind of different domain and you need to generalize. So let's go a bit more specific. So what is domain adaptation? Domain adaptation means there are two different domains, domain 1 and domain 2. But and of course, for domain 1, you have all the labels, and domain 2, you have unlabeled samples, right? But actually, at deployment stage, you actually do see a bit of domain 2 samples, okay? So you can train your model on domain 1, but still you can kind of try to adapt your model to a bit of unlabeled samples from domain 2, and then try to generalize to domain 2. Okay, so for example, people try to do feature alignment. So for example, they learn domain 1 kind of model, and then align their intermediate representations to the statistics that you get from domain 2. And then you tend to get a little bit of improvement in that case. Now, what do we exactly mean by domain generalization, which is different from OOD generalization for some reason? Domain generalization means you have multiple domains during training. And actually, what is kind of a hidden assumption that not a lot of people talk about is that the development or the training set comes with the domain labels, actually. Meaning that for each sample, you know what is the data set that it came from, right? That is a kind of very important information for your model. Because, for example, if you just know that your data is composed of multiple data sets, but do not exactly know which sample is from which data set, then there's not so much you can do about it. Of course, there are some like technologies for detecting the domains without domain labels, but that's never as perfect as having those domain labels in the first place. And once you have these kind of ingredients, sorry, yes.
So, like, quick question, you can give like an example of what one would use this information for, like something that comes to mind, like for each domain, sort of center within this domain, or like.
Right. So what you said is totally correct. So some people try to do this moment matching, for example. So they look at the intermediate features from samples from each domain. And for every domain, they try to build some kind of Gaussian. They try to fit a Gaussian around those features. And then what they do is they try to kind of align the means and variance, the covariance matrices for those Gaussians, right? In that case, you're kind of ignoring the difference between the domain, among the domains in your training set. And hopefully once you do that, your model is kind of independent of any domain information, and therefore it's probably going to work well in the next domain.
But in that case, you probably like want to do some pre-processing for the new samples you want to predict on as well, but you wouldn't know what kind of pre-processing you do.
In a sense, you're learning the pre-processing here. So you can think of the layers in the model from the input to the representation as some kind of pre-processing, or it's kind of an end-to-end system which does pre-processing and representation learning. And you're kind of trying to normalize all this entire process to match the entire process for all the domains. And then you kind of learn to kind of do the right pre-processing for the next domain as well. Okay, sure.
Does it mean you have to learn a separate representation, or a separate model that gives you representations for each domain? Or no?
Exactly. That's why you need the domain label, right? Otherwise, you need to separate them in some way, but it's never clear which algorithm you should be using. Or maybe it should be a data-driven algorithm, like model-based kind of separation. Yeah. Okay. Let's move on. So there's also test time training, which is also kind of interesting. There's domain 1 for development, and now you do deployment in domain 2, but you're actually using the domain 2 samples for continuously developing your new models, right? But you don't do any relabeling in this new domain, but still it helps to kind of have access to these incoming domain samples and then try to feed your model on the fly. Okay. Right. This is called test time training, and it tends to be more kind of get more popular these days with Alexei Efros. And now there's also continual learning. There are different types of continual learning depending on what's kind of changing over time. And now I'm talking about domain incremental continual learning. So you train your model on some domain, and then at deployment, you have several domains coming into your model, and you're slowly labeling those incoming domains. So you continuously develop your model over time, and hopefully you're kind of also not forgetting your domain 1 to 3 and so on. So your performance should kind of remain as much as high as possible as before for the previous domains, and at the same time solve the next domain pretty well. Yeah. So far we have seen cases where the task is kind of still the same across development and deployment. But now people also talk about cases where the task is actually changing. So we have cases where like ID generalization is, of course, you have the same task all the time. But now there's zero-shot learning, which assumes that you have task 1 for development, and then you have a different task for deployment. And there's no like label given for this task, okay? Like large language models are kind of doing this as well, and CLIP models, they're also kind of doing this. So with language, you can kind of encode your task information in terms of like human language. And so you in principle, there's sufficient information to kind of solve the problem. What is amazing is that large language models are kind of figuring out how to solve a new type of task, which is an output of like human creativity, like, yeah. But of course, people try to make it easier by introducing a few samples, label samples for the target task during deployment. For example, introducing case samples for a class. So you have task 1, which is kind of used for, let's say, pre-training your model. And then they have case samples for the target task that matters. And yeah, and then there's k times the number of classes samples for task 2, okay? You can do fine-tuning of your model or linear probing, things like that. And then there's meta-learning, which is when you have multiple tasks during deployments. So the reason why you introduce multiple tasks is because they wish you to learn somehow some task generic or task generalizable kind of features. And based on that, they still need some case samples from the target task because unlike OOD generalization, if there's zero information about target task, then it's super hard. Although there's learning as well. But since this is generally very hard, you normally introduce some case samples per class. And then there's continual learning as well, which is task incremental. So unlike previously, you have more and more tasks over time, okay? And ideally, you should not forget what the previous task was. Right. So it's kind of an exercise, right? So can you describe a convincing real-world scenario for the following kind of setting, right? So during deployment, you have multiple image data sets, which are all kind of different. And at deployment time, you have a new kind of distribution. So, so the question is, can you come up with an example real-world scenario for this? So this is probably going to be part of the exercise 1, okay? Now, I think this is also a very important topic. Machine learning development as some kind of system, a closed system, right? So I like to make an analogy between thermodynamic system, which is supposed to kind of keep your energy or matter in the system kind of not decreasing or increasing. And I think the same is true for information. Actually, for information, it is possible to kill information by averaging things, right? If you, let's say you have like record of heights, like or weights of everyone here, and then if we average them, then we cannot recover this back, right? So in that sense, it's possible to kill information, but I believe it's not possible to add more information to a system if there is no additional information given. And the system that I mean here is the development system, which is a combination of data set, annotations given for this data set, all kinds of inductive bias, which is in the form of the architecture, model architecture, or the way we pre-process the data, or the expertise of people who have a lot of experience with training neural networks. That could potentially be part of this knowledge. So in this kind of fixed, let's say a lab, right? Lab environment where there's no data set or annotation or anything else is given to the system, then there should be no additional information. So there's no kind of change in the maximal kind of generalization performance that you can get out of this system. Okay, I'm talking about this because there are a lot of papers out there which are kind of violating this principle and try to say they're actually getting something more out of the system than what is actually given as an input to the system. Okay, so we are probably going to talk about that later on. At this stage, it's very important to talk about information leakage, but maybe we can resume in 5 minutes after taking a break. Okay. Resume it. Okay. Right. So now about information leakage from deployment. So we are considering the resources at the deployment stage as kind of a closed system, to which you cannot inject new kind of information. If you inject new information, then that should be a separate kind of setting, right? And you cannot call it in the way that you thought about it before. So when you define domain generalization as this one, for example, then, for example, you cannot use domain 4 information in particular during development. When domain 4 is actually available during deployment, then you cannot call this domain generalization anymore. And you cannot compare against the previous methods declaring themselves as domain generalization. You need to set up a new kind of setting and build a new benchmark and compare against methods that does the same thing as you do. So what are the example leakage that you see a lot in papers? There are some cases where the hyperparameters or design choices are chosen based on label samples from domain 4. Okay, so in a sense, your validation set or dev set is kind of taken from domain 4. And even worse, you also do a bit of labeling in domain 4 to measure the performance on domain 4, okay, and do hyperparameter choices. And sure.
Right. Do I understand you right? If you would not call it domain generalization anymore, as soon as you would also inspect samples from domain 4, even though you don't have labels for them? Yeah.
That would be more like, I would say, domain adaptation in that case. Domain adaptation. It's more precisely unsupervised domain adaptation. Because there also you're kind of having access to a few samples, unlabeled samples from the target domain.
But my intuition is that that's probably the more common scenario, right? That you
Yeah.
like unsample information from the main port, often you have cheap access to it.
I mean, yeah, I think it's, as you said, it's probably more practical. I'm not speaking in terms of practicality, actually. It's more about what do we exactly mean by this, right? And the consensus among researchers. I'm fully with you that it probably makes more sense to have a few unlabeled samples from deployment, because anyways, you have to evaluate your system in the new domain. And as soon as you do some evaluation, you're making use of your target domain anyways. And so maybe my argument is that there's no such thing as domain generalization in the papers that we see, or maybe we need to kind of shift the definition of domain generalization into something that does some kind of validation in the target domain. Okay. Sure.
What do you think of things like, I don't know, using fiddle embeddings, or maybe even just yeah, like pre-training one images, for example, can it all be source of research?
So it,
Some kind of time shadow information or external knowledge.
yeah. So as soon as there's a pre-trained system in your development scenario, you're introducing a lot of things into your system, actually. It's not just a single model, but the whole bunch of your pre-training data set, which is not small, right? Especially if it's a large language model or CLIP. It's like billion scale training data. And there's a lot of kind of expertise that's put into this this model. Think of the amount of US dollars spent on this, right? So the direct consequence of that is that it's hard to say if something is zero-shot learning at all. If someone says you're solving something based on large language models, right? Because you're never sure if you have seen that task during training, right? So, or you have never, like, let's say you're trying to recognize a new class that you have never seen, but you're using zero-shot learning. Actually, there is one paper from Zeynep Akata that I really like. It's about evaluating zero-shot learning in the right way, right? And then they criticize the use of ImageNet pre-training for zero-shot learning because ImageNet 1000 classes, they seem to contain a lot of things. And for certain classes, it's not zero-shot learning at all. So, but on the other side of the argument, it probably doesn't matter anymore if something is zero-shot or not, because if you're training data or this large language model or large model is containing every useful information about the words, then it's probably okay to. There's nothing new probably in the deployment systems, and therefore it's probably just fine to just have non-zero-shot learning, but I don't know, omni generalization kind of setting. Maybe we need a different name apart from that. Yeah. So yeah, I hope you see my point. It's a little tricky to convey this. For example, let's say you're doing a face recognition, right? And the primary task there is to recognize the person that you have never seen before, being able to verify that the person that you have never seen before is the same person that you see tomorrow, right? Of course, if you have seen the same person before and trained your model on that, then it's going to be much easier. But now you're just training your embeddings to kind of recognize the new person on consecutive days. So this has like, I don't know, zero-shot verification or this kind of name. But as soon as you have like billion scale identities in your training set, this doesn't matter anymore, right? Because there are, I don't know, 70 billion people in the world. And if you have registered everyone in your training data, then there's no such thing as having to generalize to unseen person, right? Because in a sense, all of you are kind of registered in the system. And we are still happy with the system because it works well for anyone in the world. So yeah, so zero shot in the large scale case gets a little bit less meaningful, and yeah. Yeah. But again, I think the focus now is probably more on the alignment to what people mean by which, right? And in that sense, right, domain generalization still has is still being used by some people, and different people mean different things. So it's, I think, important to kind of have a common understanding of what kind of resources each method is using. Okay. So some people say we should probably select the hyperparameters within the dev, right? Meaning that within those domain 1 to 3. So that's actually what's kind of proposed in this In Search of Lowest Domain Generalization paper, which is, by the way, very good paper, actually from Tübingen as well. Yeah, I'm not entirely sure if the author was at Tübingen when he wrote this paper, but yeah, you can check. So selecting hyperparameter, this is exactly what the paper says. Selecting hyperparameter should be part of the learning problem, right? And so when you propose a new method in this domain, your duty is not just about explaining your training method, but also the method for selecting hyperparameters. Okay. Yeah. So I can give you an example of a paper which is kind of leaking information from the deployment. So actually, this is the paper, and yeah, this is the paper. So it's so easy to find such a paper actually on archive. So by the way, this is not from a small group, but actually a very good group. I'm not trying to criticize what they did. It's more about like being aware of the ingredients people are using when they do research in this area. So, so they developed some methods. We don't need to really understand what the exact method is here. What we need to care about here is what kind of hyperparameters there are and what kind of ingredients they use for fixing the hyperparameters. So for example, the first hyperparameter they consider is, what is it? Feature dropping strategy. Random top activation, top gradient, whatever these are, right? It's good that they have unified the backbone, right? Which is good. And now what they are looking at here is they're looking at the generalization performance to each of the domain. So in a sense, what ArtPaint here means is that you train your model on cartoon, sketch, and photo, and then test on ArtPaint. And then cartoon the same way. It's like leave one out generalization. And they report this average across all the leave one out generalization. And they decide that, okay, top gradient is giving you the best score here. I mean, this is a perfectly valid way you choose your hyperparameter. But at the same time, this is a little bit problematic because this is exactly the benchmark. This 82.91 is exactly the test benchmark for domain generalization in this case. So if you kind of do the validation on the test set as well, then you're kind of using this left out domain for choosing your hyperparameter. So that means it kind of works well in this. It's called PAX dataset. So photo, art, paint, cartoon, sketch. So for this PAX dataset, this top gradient or whatever is pretty good. But does this kind of guarantee that this is still going to be the best ingredient for non-tox kind of cases. It's highly unclear if that's the case, right? So, and the same is true for all the other tables here, which is kind of looking at different hyperparameter at a time. And so as soon as you see these kind of ablation studies in this kind of domain where the training and test are kind of different, then you should look into what does that exactly mean in practice. Ablation studies are generally very good for in-distribution kind of tasks, but we should be very careful with ablation studies for OOD generalization. Okay. Yes. It means you're changing one factor at a time and because you wish to kind of see the contribution of each factor towards the final performance, you leave everything else the same and then change only one of the factors and see what's the contribution here. And ideally, you understand what this factor is doing, and also you do optimization of that factor. Okay. Right. So factors or hyperparameters. Yeah.
Sure.
I can only give you an example. So in this case, the factor is the feature drop strategy here. Whatever that means. Probably you do some kind of dropping of your features in your model to kind of make it regularized better. Okay. Sure.
This maybe also like the larger point that you may only use your test set once to like get a true estimate of performance, and as soon as you use your test set multiple times, you kind of are overfitting to that specific test set.
Yeah. So by using your test set multiple times, you can always overfit your test set. And if your primary aim is to actually go beyond some known distribution or something that is kind of inside your development, then evaluating one test multiple times is kind of getting away from this original goal.
Then, like for this specific problem, I interpret this in the sense that okay, they now use the test set as validation in the sense that they want to find out which method or which feature drop strategy in this example works better. And my question is, so how would you, like now this this specific data that is burned, right? You can't use it anymore to actually know if this is true or not. So like how would we fix it? We would need to draw another data set.
So
but maybe we are overfitting to the split of art plane cartoon sketch photo.
So there, I can see like two different ways to get around this. So one is to tune your hyperparameters in the training set. So if you wish to generalize well to art plane data set, for example, then you have to tune your hyperparameters on cartoon, sketch, and photo. Okay, and then measure your performance on art planes. Then that's part of your method then, right? Meaning that for a new kind of domain, then you're also going to do the same thing. You're going to find your hyperparameters in the known kind of domains, and then hopefully, because we have seen that generalizes well to unseen domain, we can also do that for a new kind of situation where you only have access to a few domains, and then you have to generalize well to target domain.
Yeah, I mean, my question is, we then never really know whether we truly perform and whether we truly generalize to the new domain.
So yeah, at some point we need some evaluation, right? Yeah, and evaluation in a sense is a kind of validation in the larger sense. And yeah, there's no easy way around that. So yeah, as you said, we have to use the test set sparingly for exactly for that, right? Like once a paper, let's say. And I know it's hard, but we should really try not to use it a lot. But this is also kind of enforced in some other even benchmarks like ImageNet. For example, the ImageNet test set is never published. I mean, the labels are never published. And also for many other benchmarks, the test set is kind of hidden from the public. And then they only accept submissions to the server, and they do the evaluation on the server in-house. So that's probably one kind of compromise.
And then after people have been working on the problem for a while, they would want a new test that they would actually
we have to constantly change the test set. As well. Sure.
Very next question, basically where we draw the line. There's this ongoing debate in the field learning, right? That if you have all these researchers looking for new architectures, for new methods, and they all evaluate against, for instance, image learning, then this is basically also like an optimization process happening, because you never see the results which don't work. You only see the models, the architectures which increase upon state of the art. So you're always pushing it further. And so there's the theory that this is basically to some degree also overfitting on a specific data set, or on a specific set, time set of data set, right? So I'm wondering, like when you say, because the architecture is also kind of a hyperparameter, right? I mean, for instance, if you keep the topic present some quantity, I can change, but I can also change more the topology or my loss function, right? In sometimes also hyperparameter. Probably there is no clear answer to this.
So maybe one conclusion now is there's no good answer to this. There is always pros and cons, and you have to kind of balance the pros and cons well. In a sense, we are trying to address an impossible problem, which is to generalize to truly unseen stuff, right? But we can never kind of make sure that it's really unseen, right? Because as soon as we see it, it's not unseen anymore. And if we don't see it, then we don't know if it's working or not, right? So it's kind of unavoidable dilemma.
What would be the method you would suggest which gives the best trade-off? Like, what would you do?
So I can suggest one thing, which is to not use test set so often, as we have discussed right now, which is clearly, I think, most practical solution for now. But now there are also appearing fields in evaluation in machine learning, which is suggesting to do non-fixed benchmark, where the data stream itself is kind of changing over time. And so maybe fair comparison is a bit of an issue because you have kind of changing target over time. But also they say it's probably fine because in human studies, for example, they have been dealing with changing kind of evaluation strategy, like evaluation set, right? And still by using statistical methods, they could always argue for statistical significance and so on. So that's probably one way to kind of get forward. I've heard that there are some methods that's using differential privacy. Actually, that's mentioned in this paper. So you can also take a look at this paper. So they suggest like differential privacy-based evaluation method, which is probably better than just overfitting to a single benchmark. So yeah, there's no clear answer, but there are some work, contemporary work on this. Okay. And yeah, this is the core kind of dilemma for a lot of machine learning fields, but this is even more so actually for various branches of trustworthy machine learning, because they try to deal with even more severe cases of generalization or tasks that you have never seen before. You're asking the model to do some task which the model is never trained to do, right? So evaluation is always a bit tricky here, and there's no way around it. We have to kind of live with that. Okay, so that was it actually for information leakage. All discussions about settings and development, deployment. And now we wish to focus a bit on the cross bias generalization. Before that, I'm going to explain based on some simple toyish case what I mean by domain generalization or cross-domain generalization. So there are two axes here. One is task axis, which is shape, and the other one is a domain axis, color. And so depending on your perspective, you may have different ways to categorize these 9 images into 3 classes. If you are a shape person, then you're going to look at the shape. If you're a color person, you're going to look at the color. But in this case, our primary focus is on the shape. The task is shape, and the color is domain. And now your training set looks like red and green. And now you wish to generalize well to blue images. This is called domain generalization or cross-domain generalization. And now what is cross-bias generalization? But before that, some examples. Yeah, I mentioned this already, right? PACS, PATS data set. They have photos, paintings, cartoons, and sketches for I don't know how many, but some classes, some number of classes. And they do leave one out evaluation for domain generalization. Yeah, there's also domain bad, which is kind of doing something similar. Well, here they are actually combining popular domain generalization benchmarks into a single suit. And there is also Wild's benchmark with several tasks and several domains. Right, just for your reference. Actually, there's also ImageNet C and ImageNet Alphabet, ImageNet X, kind of different variants of that. So C stands for corruption in this case. And for the same image, they introduce different corruptions on the same image and see how well your model is still performing on this on those images. And there's also ImageNet A and O, which are looking into some failure cases of actually ResNet 50. ResNet 50, PyTorch ResNet 50, because there's also difference between PyTorch ImageNet trained ResNet 50 and the other versions. And they particularly kind of generated this data set with respect to this PyTorch version ResNet 50. And so depending on what kind of network you're using, you're going to get different performances, ImageNet A performances actually, which is kind of funny. And now what makes domain generalization difficult? There are 2 factors that makes it difficult. So one is that you have only trained your model on red things and green things, and you're never sure what your model is going to do with blue things. So there's no easy way around this, right? Maybe we can deal with this with epistemic uncertainty, which I will talk about in the later part of the lecture. But it's simply a kind of undefined region. And the second reason why domain generalization could be difficult is because of spurious correlations. For example, your prediction of your shape may depend a lot on the color, for example. So when this kind of thing can happen is when you have a lot more samples along this diagonal, right? So you have a lot of samples which are red circle, green triangle, and blue square, right? And then the model somehow decides that, okay, color is very easy to see. So I'm going to base my recognition on color exclusively. And if that happens, then the model fails to generalize to this kind of set, because once you see blue color, what you're going to predict is label 3, because that's how it learns, right? It's identifying the label 3 with the color blue. Okay, so this is so in this case, the training set is these diagonals, and the test set is all samples in the training in the data distribution. So if that happens, the model is focusing more on rather simple queues in general, and it fails to generalize to unconventional non-training data kind of scenarios. Yeah, I hope it's clear. So this is a typical cross-bias generalization. Okay. So development stage is like this, and then deployment stage, you have to kind of recognize a diverse set of possibilities. Or in general, it's more like at deployment time, you still have more dominance along the diagonals. But at at deployment time, it comes with more constraints on every single demographic group or every single subgroup has to have similar level of performance. In that case, we can kind of equate that situation with having an equal number of population for each cell in this matrix of possibilities. Okay. So why is that so hard? ID generalization is already an ill-posed problem. This is a well-known result, no free lunch theorem. Yeah, we don't need to go into all the theoretical details here, but it basically says without any inductive bias in the dev kind of scenario or dev kind of this box, right? There should be a kind of inductive bias here to make sure that your model, you find the right model that generalizes well to the same distribution. So without any inductive bias, any model is equally likely, and therefore there is no way you can choose the right model. And OOD generalization introduces even more complication on top of that. In particular, it's cross-bias generalization. So I call this ambiguity of queues, and I'm going to talk about what ambiguity of queues means from now on. Why this problem is impossible to solve. But before going there, I wish to, as promised, I revisit this terminology attributes. I equate attributes with queues and features. They all refer to the factors of variations in the data sample. Okay, so for example, for this red circle, the two queues that stand out could be red and circle. And the same goes for this green triangle and blue square. And yeah, and there's a distinction between queue and task. So queue means any factor variation within data. So either color or shape could be a valid queue, but task is only one of them. And the task is not inherent to the data, while queue is actually inherent to the data, right? So if you have red circle here, then it's obviously red circle, but the task is only one of them. That is defined by human. That is very important. So it is human that defines what they care about in this data. Okay. So now we come up with a development scenario where the task is super ambiguous. So let's say we train a model on this diagonal data set, meaning that the color, shape, and scale, all of them are varying at once. So label 1 samples look like red small red circle, and 2 is medium green triangle, and 3 is big blue square. Because they are varying at the same time, it's impossible to see what you exactly mean by each label, by the variation of the label. Because let's say if you choose scale, you're still going to get 100% accuracy in your training set. You're going to get 100% accuracy whether you choose color, shape, or scale. So your training set is not giving you any information which one of them you should choose. But now at deployment time, you're going to have this off-diagonal cell here, a small blue triangle, and depending on what kind of Q you're picking up during training, the label could be either 1, 2, or 3. In each case, the adapted Q could be scale, shape, or color, right? So assuming sort of an adversarial selector of environment or the task selector, you may kind of completely fool your system into choosing the completely wrong Q. And as I said, task is chosen by human, right? And therefore, it's completely possible in the worst case that the human is choosing the wrong, the most difficult Q for the model. So this means that in this kind of cross-bias generalization, if you don't have any information or knowledge about the deployment scenario, cross-bias generalization is completely not solvable at all. And so if someone says they solved the cross-bias generalization without any information beyond this diagonal training set, then you should not trust this person. It's a lie. But that happens a lot in machine learning conference papers. So yeah. So when you see that, you need to kind of point that out to the area chairs. Now, under specification is another terminology that's kind of gaining popularity these days. I think it only came, yeah, I'm not entirely sure if that's some terminology that was used in some years ago as well, which is kind of happens a lot in machine learning. But personally, I have only seen this terminology from this JMLR 2021. So I guess it's fairly new. It means that for this kind of training set, like diagonal training set, the training set is not specifying what kind of Q you should be looking at. Okay, we call this under specification. And if the model is not specifying the right Q, not choosing the right Q, we say it's misspecification as well. Okay. Now, we say this is another way to say this problem is a feature selection problem. You have to select the right feature for correct generalization at deployment time. Yeah. And now extra information is needed, right, to make cross-bias generalization possible, right? So there's one way to make cross-bias generalization possible, which is to include a bit of deployment samples into the training samples, right? Then it's a little bit like a little bit of cross-bias generalization plus in-distribution generalization samples, right, during training. So you have this 99% of biased samples and 1% of unbiased samples. Yeah, it's making the problem a lot easier than just having, well, it used to be impossible with 100% biased samples, right? But now by including 1%, or some people also use like 0.1% or 0.01% of unbiased samples, it becomes possible again, but still arbitrarily hard depending on how many unbiased samples you are including into your training set. So people control this degree of unbiased samples using raw in the respective papers. So you have to also kind of be aware which value of raw they're using in those papers. Sure.
C equals 2 and the blue circle is a typo, right? Or is that some sort of
yeah. Okay.
It's a typo.
Yeah, it is a
typo.
typo.
Making some point.
No, there's no point. Yeah. Yeah, you're right. So now it's possible again, right? Although it's less exciting and less promising. Right. So domain generalization. So that was kind of one idea. And the other idea is to have domain generalization, actually, which is to introduce domain labels as well into your. So if you just have the target label here, y equals 1 and y equals 2, y equals 3, then the problem is still not very solvable, but now by introducing this domain label, which in this case is Z123, your problem becomes more solvable. So this is another direction where your problem can be more addressable, right? So introducing unbiased samples and also introducing the domain labels. So there are like two axes where we can make this more doable. Yeah, this is a bit of repetition actually. Yeah, like in domain adaptation, we make target distribution more accessible to the training development stage, which is in a sense what this is doing, right? And then test time training is also similar in the sense that you're extending your development into the domain too, basically. We can do something similar here as well, right? We can have like, we can introduce this development on bias samples into new observations that you're going to see at deployment time. And based on that, you are adapting your model to kind of new situation. Okay, actually, that's it for today. So next time, I'm going to talk a little bit more about the exact methodologies people use in those cases. So when the domain label is available or target distribution is available, what kind of methodologies have people developed for each case? And what's the core intuition in there? Okay. So yeah, instead of reading individual papers, I think it's better to have kind of overview of the field and also what kind of resources are used in common among those papers. So we'll do that next time. So summary is that machine learning is costly because it requires periodic annotation and maintenance. And therefore we really need to make machine learning models generalized well. And machine learning setting and real world scenarios we have talked about. Machine learning development setting is like an information analog of thermodynamic closed systems. So you should not expect new information to be born out of this system. And OOD generalization, particularly cross-bias generalization, can be completely impossible. Yeah, and there are some axes where this cross-bias generalization is again made possible. Okay. Okay, so this is the last slide. So to do is please send us the preferred group to the email until 3rd of November. Okay, that's it for today. Thank you, everyone.